today's tutorial is all about the gradient and directional derivative of a function. So remember, the gradient or grad of a function of two variables produces a vector field where the components of that vector field are just partial derivatives. And the directional derivative is just an extension of a partial derivative. And the flexibility with a directional derivative is that you can look at the change in f in lots of different directions. So we're going to work our way through some of the key problems today. So I've prepared a few. We'll discuss a few. So let's start off pretty simply. I'm going to start with 58, and we can have a go. So 58 has sort of three parts to it. I'm only going to do the one involving the function x, y. So suppose you've got this function of two variables, calculate the gradient of f, graph some level curves, f equals a constant, and indicate grad f at some points on the level curve. So this is a good question because it tests a couple of things associated with the gradient. Okay, so let's have a look. Okay, so the first part of the question is calculate the gradient of f. So by the subscripts, of course, I mean differentiate with respect to, so f sub x means df dx. So if we differentiate partially with respect to x, we're going to get y. And if we differentiate with respect to y, we're going to get x. So look at the output. We started with a function that is just real valued, and we're outputting some vector field or some vector valued function. Okay, that's what the gradient does. It takes something real valued and turns it into something that's vector valued through this operation. Right, the second part of the question was graph some level curves of this function. So we'll just be graphing them in the xy plane. So consider xy equals a c, which is a constant. So let's start off simply. If c is 0, what does that give you? Well, it gives you xy equals 0. So either x is 0 or y is 0. So that means you're going to get the coordinate axes in the case c equals 0. X equals 0 or y equals 0. So we get the axes, the coordinate axes. Okay, I'll draw them in a second. Now, if c, say, is anything other than 0, we can rearrange this and turn it into something we, I guess, can consider. So this then, if for different values of c, what's y equals c on x going to give us? What kind of curves? Hyperbole. Yes, very good. Hyperbole. So okay, so let's draw some in the xy plane. Okay, so the coordinate axes are the case c equals 0. Okay, so for say c equals 1, we're going to get something like y equals 1 on x. So that's going to be like that. Okay, c equals minus 1. Okay, so we're going to get these kind of curves. Okay? So I've drawn in a few of those. You can keep drawing them in if you want to, like this, blah, blah, blah. Right. Now the final part of the question, part C, whoops. Indicate grad f at some points by arrows on these curves. So you've got a vector field here, and you want to draw in the associated vector at some point on the curve. Okay, so I'm actually going to choose a simple case. So I'm just going to redraw this. Now, what's the relationship between the gradient, or grad f, and the level curves? Who can tell me? What's the geometrical relationship? Yes? Right, they're normal, right? So if I just consider, say, the point 1, 1, this gradient vector is going to be the vector 1, 1. So if I draw it in, it'll go from here to here. And I'm noting that the gradient vector is perpendicular to the level curve, okay? So if I was to draw, say, a tangent vector in there, I would get a right angle. Perpendicular or normal to okay, let's draw in another one, just to, for a little bit more completeness. So here's another level curve. This corresponds to the case c equals 0. Well, at this point, at the point x equals 1, y equals 0, my gradient vector is going to be 1, 0. So it's going to point straight up like that. Okay, sorry, I know the writing's a bit small there. Again, it's perpendicular to the level, that particular level curve. Any questions? Okay, you can draw more in if you want to. You have another one, you'll have another one, say up here, and it'll be pointing that way. Okay? Who did that question? Who's already done it? Okay. Anything you'd like to add to the solution? Okay? Oh, that's all right. That's okay. All right, let's move on to another one. 59. Anyone done 59? Anyone? On the surface, it looks a bit Looks a bit difficult. But I guess there's three different sort of sub-questions. There's a long way and a short way of doing these problems. I'll do part A the long way, and I'll do part B the short way. Okay, just to give you a bit of flexibility in your methods, I guess. Okay. So we have defined a vector function by the following. So we've got this vector function R is just the position vector, basically, of any point in space. Okay, so technically it is a vector function because it maps R cubed into R cubed. So you put in a vector, you spit out a vector. Okay? But it's just the position vector of what you put in. So it's not a big deal. Okay? And this function R with no tilde is just the magnitude of this vector function R with a tilde under it. So it's helpful if you can really distinguish the difference between, having a tilde there and no tilde there. It makes a big difference. Okay. So in the first part, we want to show that grad R equals 1 on R times the vector function R. Now, I'm just going to rearrange this and sort of prove an equivalent. So I'm just going to bring the R up the top. Okay, so firstly, let's try to understand what this boxed, starred identity means. Okay, R is a real valued function. So I can take the gradient of it and produce a vector. I can then take that vector and multiply it by a scalar valued function, a real valued function. So on the left, I've got a scalar times a vector, which is, what's that going to give me? A vector. And on the right-hand side, I've got a vector. So the equation certainly balances in terms of vectors versus scalars. But let's see if we can actually prove this. So I'm just going to work with the left-hand side and show that it equals the right-hand side. Okay, so it's R times the gradient of this So what I want to do is apply the gradient operator, or I guess the del operator, to this and form some sort of vector. Okay, so I'm going to leave that R there for now. So I want to take the partial derivative of this with respect to x, that'll be my first component. Derivative with respect to y, that'll be my second component. Derivative with respect to z, that'll be my third component. So if I differentiate this with respect to x, I'm going to get something like this. Yes? If I differentiate with respect to y, I'm going to get something very similar. And if I differentiate partially with respect to z, I'll get the following. Now, notice I've got a common factor of 1 on root x squared plus y squared plus z squared, so I can actually take that out the front. And what I can do is cancel with that r, because r is just the same thing. Well, I guess it's the square root of x squared plus y squared plus z squared. So I can actually do this, and r's this, so I can cancel out. So I get x, y, z, and what's that? Oh, that's just my definition of the vector function r. So left-hand side is this. I've got it down to that, and that is the right-hand side. So hopefully you can see from that analysis, it's important to understand where am I producing a vector? What kind of multiplication do I have? Is it a vector with a scalar, or is it a dot product, or what is it? Okay, you really can't underestimate the little operations that you're dealing with. Okay, questions? Okay, that's probably the long way of doing it. Let me show you a simpler way. There's a chain rule involved with this. So let's move on to part B. So using the same notation as up here, part B, aha. Part B wants us to show the following. So, oh, and actually, sorry, part B actually just wants us to calculate this, okay? And like I said before, there's a quick way and a slow way of doing this. So let me show you. So calculate the gradient of cos r. Okay, so if I write that out just in this kind of notation, you can hopefully see that I've got a function of a function here. I've got the cosine function, and I've also got the function root x squared plus y squared plus z squared. Now remember, the gradient involves partial derivatives. So if I'm going to take partial derivatives, maybe there's a chain rule I can use. Maybe there's a chain rule I can use. Well, that's what I'm going to show you now. You can use a chain rule if you want to. Of course, you could just go through and do it the standard way, but let me show you something different. Okay? So we've got a function of a function, f of r. Now that is just f prime of r times gradient. Oops, sorry, there's no tilde there. Okay, this is just no tilde. Okay, so you've got a scalar function multiplied with a vector. So all we really need to do is work out, well, if f is the cosine function, what's f prime? What's the derivative of cosine? Negative sine, right? So that's pretty easy. And then we've actually worked out the gradient of r from the previous question. So we know what that is as well. So working out this, Okay, it's the derivative of this, so negative sine along this times the gradient of r. Okay, and we already worked out the gradient of r from part A. Yeah, so I've sort of mixed up my notation there a bit. Let's put it all under the one banner. Now, of course, you could go through just do it in the way I did part A. Just don't worry about any chain rule or anything like that. It will still work. But this is a lot easier, and it gives you, I believe, a better oversight into how to generally solve these problems. Why make more work for yourself when you don't really need to? You might think, well, you know, I understand it better if I just do it the long way. No problem. Okay, it's up to you. Okay, so I'll leave part C for you guys to do. Let's have a look at directional derivative. Okay, so we're going to look at 60 now. So we've got a whole list of functions and a whole list of vectors. And I guess these V's are supposed to be, I mean, they're vectors here, but I mean, I guess technically they're supposed to be points, right? Compute the directional derivative for the given function at the point associated with this vector in the direction of u. So, as long as our function's differentiable, right? So it's like a polynomial or some sort of, you know, perhaps a cosine or sine function, something like that. We know that the directional derivative is just a dot product, right? It's a dot product between the gradient and the u hat. So that's an important thing from a computational point of view. So I've chosen D actually to do. So let's discuss that. Anyone done D? Anyone? How did you find it? Good? Good learning? Excellent. Would you want to step us through it? How did you do it? So let me just write this out, and we'll get the. So I'm actually going to let P be this point, and U is just this vector. So step us through it. Took the gradient of f, yes? Okay, so why did you take the gradient of f? Huh? Yeah, why? Because we need it. Why? Sorry, say again? Yeah, that's all right. So we want to we want to compute this directional derivative, right? And we know that because our function's differentiable, we can use dot product. Yep. So it's just this dotted with this. So there, let's do the gradient first. So let's take grad f, right? What do we get? Okay, so yep, so it's just f sub x, comma f sub y. So 2x, 2x e to the x squared plus y squared. What about the other component? 2y. Yep. Okay, so now what? evaluated at the point, yes? Minus 1, 1. So the first is going to be something like minus 2 e to the 2. Yep. And the second component, what's that going to be? 2 e to the 2. All right, so we've got pretty much half our bit. Now what? The unit vector. So the first question is, see how this relies on a unit vector. Is this a unit vector? No. Okay. Does it have length 1? No. Well, so we just form a unit vector by, I guess, dividing by its magnitude. So what's the magnitude of this vector going to be? Root 5, right? Yeah. So you just square the components, add them together, and take the square root. So now what? We're on the home stretch. Yeah, the dot product of our two vectors. So we want to take the dot product of this with this using this formula. Dotted with this. So I'm going to take that 1 on root 5 out the front. I guess I can take the 2 out as well. So I'm going to get minus e squared plus 4 e squared. So then that should be like a 2, shouldn't it? Yeah. Okay. All right, so that should be minus 2 or something like that. No, just 2. All right, assuming we can do our arithmetic, you would have been all right. Sorry about that. Okay. All right, so that's the question. The other questions in 60 are very similar. Okay. So, well, that's just a number, right? So it is a value. Yeah. Yep. Yeah. So if we wanted to put this in some context, if I'm standing at the point P and I'm looking in the direction of U, right, is the surface increasing or decreasing in that direction? Why? You correct? But why? Well, I guess you don't even, just from this value, I can tell that the function's increasing in that direction because it's a positive value. Okay, and we'd sort of think, okay, well, if it's some sort of derivative, you would expect, and it's positive, you would expect the function to be increasing. Okay? So you're right, and you can tell by the sign on the value here. Okay. Okay, let's have a look at 62. Now, we've got a mountain that's very conveniently expressed by this function h. It's lucky, isn't it? And we're given the scenario of a bushwalker who wants to climb this mountain where x, y, h are in meters, x-axis points east, the y-axis points north. The bushwalker is at some point P, which you're given the sort of coordinates. So the x-coordinate would be minus 400 and the y-coordinate would be minus 1600. What is the slope of the mountain at the point where the bushwalker is in the direction of the peak? And in which direction at P is the slope the greatest? So let's see if we can deconstruct this and see what's going on here. Anyone done this question? Okay. All right, good. So, 62. And so here's our function h in meters, and our point of interest is here. Now, if we're standing at that point and we're looking in the direction of the peak, first of all, the question is, where is the peak? And secondly, what's the vector associated with it? So let's look at our function h. Where does h have its maximum value? Right, why? Why does h have a maximum when x and y are both 0? Yeah, exactly. So we've got some value, some positive value, and we're taking away some other value that's always greater than or equal to 0. So the way of minimising this is just plug in x equals 0, y equals 0. So that'll maximise the h. So all right, so if I'm standing at okay, this isn't probably drawn to scale. If I'm standing at this point here, what's my vector pointing towards the peak going to be? So I'm at the point P, I'm looking towards the peak at the origin. What's the associated u vector going to be? Huh? Say again? Yeah, well, I mean, even, like, all you have to do really is look, yes, so you're right, but, I mean, technically speaking, you'd want to have the whole vector in here, right? So the vector would be, okay, so something that starts there and is pointing that way, 1600, 400. Okay, if you're worried about that, just work out the vector PO. So this is just the vector PO. Okay? So is that a unit vector? No. So we have to make it a unit vector. We're going to get some messy values here. Okay, so again, just calculate the length. Now, if you square these values, add them together and take the square root, just going from one I've prepared earlier, you'll get 400 times root 17. Okay. What else do we need for this problem? If you want to calculate the directional derivative, we need the gradient. Okay, we've got our unit vector, but let's calculate the gradient as well. So grad h. So let's take the partial derivative. That 400 is going to disappear. So I'm going to get something like this. Now I could have simplified this, but I just chose not to. So at our point of interest, P, we need to plug in our x values at P. What are you going to get? You're going to get something like 3,200 over 10,000, and the other one's going to be 3,200 as well. Oh, how convenient. Okay, now of course you can cancel off. So, the directional derivative. Sorry. So not doof, it's going to be doof. So it is the following dot product dotted with our unit vector. Okay, so if we work this all out, just basically replacing this with this and simplifying, that root 17 is going to stay there, but you should get the following. So that is the slope of the mountain, that value, 8 on 5 root 17. That's the slope of the mountain at P in the direction of the peak. So part B then is, in which direction at P is the slope the greatest? So you're looking here, you want to know which direction is actually the, maybe the worst place to, or the most challenging direction to climb, let's say. So, anybody know how would we calculate the direction at P where the slope of the mountain is the greatest? Anybody remember? Yes.
Is it in the direction of the absolute value of the gradient?
Oh, you're almost right. Why the absolute value? So you're right. It's in the direction of the gradient, the same direction as the gradient, right? So you wouldn't put the absolute value in because we still need a vector, right? Yeah. So you're right. So yeah, that's it. Basically, because the dot product involves an angle between the two vectors, you can maximise that by choosing, the angle to be 0. That'll give you cosine theta equals 1. So that's where the maximum sort of directions derived from. So let me have a look at this. So part B, so at P, H increases most rapidly when the angle between the two vectors, grad H and the unit vector of direction, H. Okay, so we can actually just go back now and look at what we've got down here. Okay, we can obviously cross off some of these zeros. that's the same direction, well, that's going to be the direction that we want, right? So I guess I'll take that out front. Okay. I'm not going to, I can simplify that, but I'm not, there's no need to. So the important thing here is that these components are equal. So in a sort of, what sort of direction will that vector u be pointing in? Well, for every sort of, I guess, 1 unit we go towards the east, we have to go up 1 unit, right? So this vector is just going to be pointing in the northeast direction. Okay, so what's the direction of the biggest increase? Well, it's in the northeast direction. So if the bushwalker starts walking northeast, he or she will be challenged. Let's go out with a bang. 66. Suppose we have a differentiable function. 66, by the way. Anyone? Suppose we have a differentiable function which has at some point a directional derivative of 1 on root 2 in the direction of this vector 1, 1. In addition, suppose that same function, f, has a directional derivative 1 on 5 in the direction of this vector. Find the gradient of f at, I guess, at the point associated with the vector u. So 66. So making all the assumptions in the question, we have the following. We know that actually, yeah, sorry, that should be a v. Let's put that as a v. So the first bit of information can be written down like this. We don't know what P is. And the second bit of information, let's call the vector W in that case. So the directional derivative of f at the same point in different directions is given to you by these values. So now what we're going to do is form 2 equations and 2 unknowns. The idea is to calculate or find, I guess, this. All right, so let's look at the first piece of information. It's just the dot product of the partials at P with a unit vector. So the unit vector associated with this is going to be this. And similarly, you do the same thing for the second case. So you're going to, let me put that in there. Yes. So the second case, the length of that's going to be 5. So it's going to be when you take the dot product. Okay, I've jumped a few steps there because I'm running out of time. So now you have 2 equations and 2 unknowns, 2 simultaneous equations. You can solve for f sub x at P and f sub y of P. you're going to get f sub x of p equals 3 and f sub y of p equals minus 2. Thus, our gradient is just this. Okay, so I've done that rather quickly, but I'm out of time. So.